All right, hi guys. This is the Zaption for lecture number 4, which is on page 19. So our target is target 3. So we're moving on. It says I can analyze centripetal acceleration, tangential velocity, net force, and period using Newton's second law. So we're combining Newton's second law with our ideas for circular motion. All right, so let's talk about that centripetal acceleration. So last time we talked about notes, we talked about acceleration being the idea that you can change your direction. So we might be moving at a constant speed, but our velocity is changing because we're accelerating. We can't use our regular idea of velocity or of acceleration because that was change in velocity divided by time, because we're changing direction, not speed. So we need a new equation in order to calculate acceleration. So this is our equation to calculate acceleration. We use the tangential velocity, square it, and divide it by the radius of a circle for whatever our object's moving around. So it's based on the changing of that velocity because your radius should stay constant. So this gives us centripetal acceleration. So in your packet it says which variables are directly related to AC, which are inversely related to AC. AC is centripetal acceleration. Well, AC is already isolated, so we don't need to rearrange the equation. So it would be directly related to the v squared, the velocity, because that's in the numerator. And it's inversely related to the radius because the radius is in the denominator. So again, we don't have to rearrange. So the next part of your packet says which variables are velocity directly and inversely related to. So v, we need to rearrange the equation first. So let me move me out of the way. Up there. Maybe over here. Sorry about that. Okay, so we're going to rearrange the equation. I will multiply r to both sides to get v squared by itself. So v squared equals ac times r. Now looking at this, it's directly related to both of these, right? They're all in the numerator. So the direct relationship would be acceleration and radius. And there's no inverse relationship because there's nothing in the denominator. So we'll try the next one. What variables are directly related to r? So let's get r by itself. So I would divide both sides by ac. Then you would get v squared divided by, this is ac down here. And so it looks like the direct relationship would be between r and v, and it would be inverse between r and ac. So velocity is directly related to r, inversely related to ac. You don't want to memorize these ideas. You really just want to understand that when we're talking about direct and inverse, we need to isolate our variable and then look at numerator versus denominator. All right, so let's assume a car is driving around a circular track of radius r at a constant speed of v and has a centripetal acceleration of this, okay? So given v and r, this would be how you would calculate the acceleration. How would the acceleration change if it went around the track 3 times faster? So if we change this variable to 3 times faster, what's going to happen to the acceleration? Well, I know these are directly related, right, because they're both in the numerator, so acceleration is going to go up. How much will it go up by? Well, if I plug in 3v squared, that square there is the same like we had before. 3 squared would be 9. Okay, so it's going to increase by a factor of 9 because we plug in a 3 here and 3 squared is 9. What would happen if it went around a wider track that had 3 times the radius? So now I'm putting a 3 down in the denominator. Well, acceleration should go down because there's an inverse relationship here. How much is it going to go down by? Well, it should be 1/3 because this isn't squared or anything. So just 1/3, decrease by a factor of 1/3. How would the car's centripetal acceleration change if it went around a track that had half the radius, but it's going at 1/3 the speed? I want you to go ahead and try this one. So we're going to change radius to 1/2 and velocity to 1/3. So try calculating that out to see what's going to happen to the acceleration. Pause me and go. All right, hopefully you got 2/9. Can't see that math. Let's see if I can move this down. Oops. So if I scroll this down right here, you can see that math. You get 1/3 squared over 1/2. So 1/9 over 1/2, which is the same as 1/9 times 2, because dividing by a fraction is the same as multiplying by its reciprocal. And so you get 2/9. Awesome. All right, moving on to page 20 in our packet. So this is an example. We want to calculate the centripetal force. So centripetal force is the net force So see that keyword, centripetal force is the net force, making something go around in a circle. Because net force equals ma, we can use Newton's second law to find that. And if we want to remind ourselves that we're using force and acceleration for a circle, we can call FC and AC so that we remember that it's centripetal. That's just a shorthand for that. All right, so first things first, I want you to draw a diagram of the shuttle orbiting the Earth. What is the centripetal force that keeps the shuttle from flying off in a straight line? Draw this force in your diagram. So let's go back. I'm going to draw this for you. So let's say we get, here's the Earth, okay, and I'm going to make my shuttle a star because it's hard to draw in here, okay, and the shuttle's going in like this path. It's supposed to be a circle, not a very good circle, okay. So if you remember from our lab the other day, we want to know what the centripetal force is, so we can draw that centripetal axis, which means just straight towards the center. And what force is pulling this towards the center? Well, that's going to be gravity, right? Fg, because that's what's keeping this satellite shuttle in orbit, Fg. So that would be what the picture would be. And then calculate the force. So if it's an Fg, we can use Newton's law of gravitation. So big G, m1, m2 over r squared. So why don't you pause and try and solve for that on your own, and then we'll go through it. So pause now. Okay. So you have that equation. You plug in 6.67 times 10 to the negative 11th. m1 is this, m2 is this. You need to add up the height and the radius of the Earth, right? Because we're above the Earth's surface, so how far to the center of the Earth. And then divide it by those two added together squared. And you should get, let me go back to my pen, go with green, 1.02, this is a point, times 10 to the 6th. Okay, so that would be the gravitational force between the satellite or the shuttle and the Earth, and between the Earth and the shuttle, right? Because those forces are equal. All right, let's move on to page 21. So now that we know the force, let's calculate the shuttle's centripetal acceleration. And we want to look at, does it seem like a big acceleration, a small acceleration? What does it tell you about the shuttle's motion? What direction is it? So first, let's calculate the shuttle's acceleration. So what we want to do is do F net equals ma. We know the force. We're going to divide out the mass. So here's the force. We can divide the mass, and you get 8.8 meters per second squared. Okay, does that seem very big? Seems pretty close to 9.8, but definitely smaller because we're further away, right? What does this tell you about the shuttle's motion? This should tell you the rate at which the direction is changing over time. And that's kind of confusing because it's meters per second squared, but it's, remember, we're accelerating in a circle at a constant speed. So it's telling us the rate of change of direction over time. What direction is the acceleration? You should understand that this is a centripetal acceleration, so it's pointing towards the center. So now I want to know, what is the shuttle's velocity? How fast is it going? What direction does it point, and is it pretty big? So we're going to use this equation right here. So I already calculated AC, right? I got that from F net. So I can say equals v squared over r and solve for the v. So we get 8.8 equals v squared over the radius, so both of those added together still. So I'm going to add those up and multiply to the other side. That equals v squared. Since it's v squared, we need to take the square root of both sides. And you guys can't see that. It says 7,696.9 meters per second. That's the velocity of the shuttle. Is this pretty big? I would say, yeah, that's a really fast velocity for this to be moving in. What direction does it point? It's going to point tangentially, right? So off at a tangent, whereas the acceleration was pointing towards the center, this is going to point off at a tangent. Last example on here, we want to calculate the periods. We talked about this on the first day, but we haven't talked about it since. Period is the amount of time to complete a circle. So I asked you guys, what is the period for us to go around the sun? And we said 365 days. What's the period for Earth to rotate one time? 24 hours. So we're trying to figure out the period it would take to complete one circle around the Earth, this shuttle. So for our satellite, how long does it take to orbit the Earth one time? So to calculate this, we are going to use the idea that distance equals rate times time. So the distance that it's going to travel is equal to how fast it's going times how much time, okay? So since we've got that, the distance it travels is a circle. And so the circle, we need to find the circumference. So 2 pi r, so 2 pi times that distance for the radius that we've been using. Again, we're doing that since it's a circle, so the distance we need is going to be the circumference, 2 pi r. That's the distance. We know the velocity is 7,696.9 times time. Solve that, you get time is 5,495.7 seconds minus 91.6 minutes. Oh, sorry, that's not minus, that's equal. So this is how many seconds. Not very useful, I don't know how many seconds that is. But we can divide that by 60 to figure out how many minutes and divide it by 60 again to find out how many hours. So it takes the shuttle 1.5 approximately hours to go around the Earth. That's fast, like that's insane to go around the entire Earth one time. It only takes an hour and a half. That's pretty cool. So yeah, so that is the idea, big ideas here. So make sure you understand centripetal acceleration points towards the center, tangential velocity points out, and that the idea of period is how much time it takes to go around. And since it was a circle, we used 2 pi r. If you've got any questions, watch this again. Make sure you answer the questions at the end. Thank you very much. Bye.